Swayam Prabha. Digital India. Educated India.
Welcome to today's lecture. In the last few introductory lecture, we got ourselves introduced to the mineral deposits. We will take a very quick brief recapitulation to the salient aspects of mineral deposits that we discussed. As we know that mineral deposits are the result from the earth's own beneficiation process, and they are distinct and they are discrete, and they are parts where they are the enriched part in the earth's crust and occur in association with common crustal rocks. They can be called as anomalies in the earth's crust because concentration of any metal of interest is higher than the surrounding, higher to the extent that they can be economically exploited, and they occur distinctly in variable dimensions. Sometimes an ore body can run for more than 100 kilometer in strike length, sometimes it may get terminated within a few hundred meters in strike length. Similarly, in the depth and width dimension also they are variable, and we see the whole spectrum of mineral deposits of many different metals and non-metals in the upper continental crust. The available quantity of any metal of interest, as we have seen, they vary in millions or billions of tons, taking abundant metals like aluminum and iron, which the quantity vary in terms of billions of tons, and scarce metals like the gold, platinum group of metals, uranium, they are only a few millions of tons or thousands of tons, and this can be explained as a fundamental control exerted by the abundance of these elements in the ball crust and in particular in the continental crust, and they obey something which we call as an enrichment factor. That means the minimum grade, minimum value of the metal, minimum concentration of the metal, which makes it an ore divided by the average crustal abundance, something like Clark. We can calculate a value and say that by how many times that particular metal has to be enriched to form an ore body in the crust. We saw that there is a general non-uniformity in distribution in space and time of these mineral deposits all across the continents, and as far as the distribution in time is concerned, we do see some variation, significant variations going from the older era to the younger, to the newer era, and with the thing in mind that most of the continental crust are covered by rocks which are old, the Precambrian rocks, and thus we get the deposits from them which are also of that comparable age, and these ore deposits are a result of a very complex interplay of the lithosphere, hydrosphere, atmosphere system, which has been evolving parallelly with the evolution of the continental lithosphere, and that is how we see variations in the nature of mineralization of different metals, or we take the different types, genetic types of different metals and the different genetic types of the same metals. Mineral deposits are a result of operation of earth's broad processes, which are the endogenic and the exogenic process which we discussed. The endogenic process, the energy being derived by the earth's own heat engine, and the exogenic process being mainly driven by the sun, which are the surface operating process, and they can be somehow linked because as we discussed, many of the surface operated process, the weathering erosion process are much faster, where there are active continental uplift and active continental margin situations compared to parts of the continents where there has been peniplanation or there is no much of active tectonism going on, and although they are products of the Earth's broad processes, the deposits vary in their size from hundreds of kilometers square area to even sometimes within just about a kilometer square in size. So, that makes us believe that in addition to the processes which are operating on a broader scale, larger scale, there are also some local scale controls which are exerted in actually giving rise to the enrichment process in many such cases. And the diverse mineral deposits occurring in their different mineralogies can be understood from the very basic nature of the metals or the elements, their geochemical classification, and the enrichment that took place in subsequent stages of fractionation of the planetary fractionation, such as the core, mantle, and the crust. They give us the basic understanding behind the principles of mineral deposit formation, although there may be some amount of queries, some queries which remain unanswered, because for example, we know that during the core mantle fractionation most of the iron was partitioned into the core. At the same time, we get huge quantity of iron is available, finally forming ore deposits in the continental crust. So that would lead us to believe that this fractionation process was either incomplete or something else happened after the formation of the core, sometimes which is also talked about in the context of gold. Gold being a siderophile element is also supposed to have partitioned into the core, but we do get the quantity of gold that we get in the form of deposits or mineral deposits, which might have been derived from the mantle, that led to the proposition of hypotheses such as the late veneer hypothesis, by which the later materials which accreted to form the earth gave the necessary metals to form their mineral deposits. The deposit forming processes operate within 10 to 15 kilometers up to a depth of 10 to 15 kilometers in the crust, but only when they are exposed within the top 5 kilometers they are accessible to us and we are able to recover them, we are able to economically exploit them, and there are surface operating processes within the top 5 kilometers of the earth's crust. And so many and the suitable locales in the earth's crust, there could be a recent or the ancient sedimentary basin, whether the basin could be deformed or undeformed, could be a basin marine as well as continental derivation, which are the areas or the zones in which deposits of various metals are found to occur. There are zones of brittle ductile deformation such as fault zones, shear zones running for several hundreds of kilometers, crustal scale features within in the vicinity of magmatic bodies. These are the important locales in which we see the mineral deposits. In addition to that, the surface operating process, the major river valleys, the present day ocean basins where there are mineral deposits, active mineral deposit processes are in operation, which we looked at few of the features, such as the processes that are operating on the mid oceanic ridges and also in subduction zones. We also discussed that one of the important fundamental attribute of any ore body or mineral deposit is the mineralogy, and this mineralogy gives us the first hand information about the physicochemical environment of formation of mineral deposits. The physicochemical environment we define by using various intensive and intensive parameters such as temperature, pressure, and the compositional parameters such as the fugacity of gaseous species such as oxygen and sulfur. The important chemical parameter in an aqueous environment is the activity of the hydrogen ion, that is the pH, the concentration or the activities of the various anionic and cationic species, all that, even including the metals which form their mineral deposits. And what is the systematic study of a mineral deposit? The very first information is obtained from the minerals that they constitute the ore body, and from the mineral, by systematic study of the minerals under the microscope, studying their intergrowth, the textural relationship between them, the paragenesis or the paragenetic sequence, is deciphered. And just giving an example, let us say that we have and we use this paragenetic sequence to explain the different the intensive and the extensive variables, and sometimes we plot them in different types of phase diagrams, such as the temperature and composition diagram, pressure temperature diagram, temperature versus log FO2 diagram, or temperature versus log FS2 diagrams, and so on, to interpret the environmental parameters. Just to give an example, we can consider some isothermal isobaric conditions P and T fixed, and we can, for example, we just take a simple example of a system in the Fe, S and O system. There we can this is pyrrhotite FeS, this is pyrite FeS2, this is magnetite, hematite, and in this FeSO system we can write the reactions between pyrite and pyrrhotite. For example, we can write a reaction of pyrrhotite plus half S2 giving rise to pyrite, in which we can have this when we write an equilibrium constant K, we put it in this way. By convention, we take the thermodynamic concentration or the activity of the solid species is equal to 1. So, K reduces to 1 by, and when it becomes a gaseous species like sulfur, we express it, the activity, the thermodynamic concentration of the activity is expressed as fugacity, which is the corrected partial pressure for that gas. So, we will put it as F S2 to the power half, and this equilibrium constant at this pressure and temperature is known, from which we can calculate that what will be the value of log Fs2 corresponding to the pyrite and pyrrhotite boundary, and we can plot it here, and then we can construct similar diagrams, similar reactions, such as pyrite plus oxygen giving rise to magnetite plus sulfur. We can balance this equation, and then in that case the log K, here the log K will be depending on both oxygen and sulfur, and we can find a relationship of log Fs2 will be equal to something like A plus B into log FO2, and for a range of log FO2 value we can calculate the value of log Fs2 and can plot here, and similarly can draw the boundary between pyrrhotite and magnetite. Similarly, for magnetite and hematite we can write Fe3O4 plus oxygen Fe2O3. So, this will be 2 and this is 3 half. So, here only variable is the oxygen. So, fugacity of oxygen can be taken, and this boundary between magnetite and hematite can be plotted. Now, so this becomes a phase diagram, isothermal isobaric phase diagram in an FeSO system, and if it is an isothermal isobaric, so we know that nu is equal to C minus P. Nu is the degree of freedom and C is the number of components in the number of phases. So, for an invariant point, like this is an invariant point, this is an invariant point, and on these invariant points we get the 3 minerals like pyrite, pyrrhotite and magnetite to be coexisting. These will be the univariant lines on which 2 phases will be coexisting. For example, this is a stability, this is a boundary for pyrite and magnetite, and these fields will remain as the bivariant fields where only one phase will be stable, for example pyrrhotite. Now, if we extend this particular system including a species, another species as copper, then it is going to give us the stability field of other minerals like chalcopyrite, bornite. Just for example, this becomes a boundary for bornite plus hematite giving rise to chalcopyrite. This is a boundary bornite plus magnetite giving rise to chalcopyrite. So, here we define a stability field of chalcopyrite, and in these cases when copper is included as one of the components, these bivariant fields will become phases where areas where 2 phases will coexist instead of 1, and similarly we can define the invariant points as number of components becoming 4. So, number of phases also will be 4 on these kind of invariant points, and we can interpret the variation depending on the what mineral paragenetic sequence you can establish. For example, if we get a dominantly a pyrite magnetite mineralogy giving rise to hematite, we can always think in terms of increasing FO2 and FS2 condition in this environment, and similarly we can use these diagrams, this kind of reaction relationship using standard state thermodynamic data to retrieve the environmental parameters. So, this is one example. We can extend it to any number of components including the species like potassium, silicon and iron, and can also find out the stability field of the silicates, and can explain the assemblages in which ore minerals also occur along with the silicate minerals, and the reconstruction of the physicochemical environment becomes even more precise with those kind of by increasing the number of components which will be more close to the situation in nature. So, based on the rock ore association, tectonic environment, sources of metal and other essential constituents, and the working out of the details of the local scale processes. So, mineral deposits are classified into various genetic types, and there are many hypotheses of the mineral deposit formation that have been proposed, and such hypotheses are still in the process of refinement because discovery of new type of deposits, observation of new types of features which were not seen before, or the explanations were not available because of some limitations. So, and if we now from here, if we go into the looking into the different types of deposits that form in different types of as a result of different type of processes, we see that the amount of information, the getting into the minutest details of such deposits will become dauntingly vast, and it will be the scope of this lecture series will not allow to go into the much finer details of this, but we will present a broad overview of the many types of deposits which result from the broader processes, and so that we just get a basic understanding of them in terms of the process, in terms of the deposit characteristics, and look at what are the working hypothesis or working or the understanding of their origin and the evolution of these deposits are. So, from here we will go to discuss the very first major or the most well known of the processes that operates in the Earth's crust, in the lithosphere, and also in the deeper parts of the earth interior in the asthenosphere. And we look at as how we look at magmatism as we define the mineral deposit forming processes is Earth's own mechanism of beneficiation. So, we will see how magmatism is a process, or how effective or how efficient magmatism as Earth's own beneficiation mechanism. Now, to understand magmatic processes, we have to answer some of the basic queries, even though it may be very common knowledge when we start studying this geology at an elementary level. So, the first question is why rock melt? Why rocks melt? Rocks will melt. We all, this is a rock. This rock could be anywhere, could be in the middle of the crust, in the shallower level of the crust, deeper in the deeper part of the crust, or in the upper mantle, and depending on that the rock is of different composition. So, this rock has to melt. So, the melting process, if we would like to see it very fundamentally, then we can crudely define situations like this. This is temperature, this is pressure. So, it would indicate, or it represents we are going deeper, and higher temperature we are encompassing, and something like we can define crudely. So, suppose this is the geotherm. The increase in temperature with depth as we go to the deeper part of the crust, and something if I just draw a crude curve over here, which could be the melting curve. We know that rocks will remain solid under the given pressure and temperature condition, and anything that to the right of this curve will make the rock melt, or the rock is present as stable solid on this part of the. So, that there are many ways in which this solid rock would melt. Number one is that we would increase the temperature, take it to the right, or we can say that the conditions corresponding to intersection of this melting curve with the geotherm will make the rock melt. If we are anywhere here, we could either go up to a situation like this or like this. So, that means if we are following this a path like this one, that means we are decreasing the pressure, and we are essentially creating something called a decompression, which happens in the when the asthenosphere rises on the mid oceanic ridges. It gives rise to the rock of the mostly a peridotitic type of mantle rock, which melts because the pressure is released because of this decompression with the rise of the convection cell as we know them. We could possibly add some more extra heat from somewhere and make the rock melt. There could be many other possibilities, but the situation is that we are able to melt a solid rock, giving rise to a molten material, and then let us think about, so where rock melt, rock would be melting anywhere in the any intermediate depth in the crust, in the mantle, and there are many zones. We see melting taking place in subduction zones, melting taking place in mid oceanic ridges, melting taking place in mid continental rift zones, and so on. And when the rocks melt anywhere in this region that we have defined, when the rocks are melting, so the melt, how we describe this melting process? We describe this melting process as something we called as partial melt. Means when we melt a rock, it actually it gives rise to a small fraction, depending on, it gives rise to a fraction of melt, and it leaves behind a solid residue, and that is why we call it partial melt. So, all melting processes within the earth's interior are essentially partial melting, and depending on the parent rock composition, we get the melt which are of different composition, which can be explained on the basis of the mineralogy of the source rock and the temperature and pressure conditions of melting. And there has been all work done in understanding the melting behavior of different types of rocks in different types of conditions. Sometimes when we are discussing this kind of melting process, sometimes we find that the solidus, which basically the melting curve that we are drawing here, sometimes the solidus moves towards the left if there is fluid present in the rock, which happens in many situations, which we will not be discussing in detail here. But what will be more relevant to us here is to discuss as to what is the consequences of this melting process that is relevant to mineral deposit formation, because the mineral deposit formation we are concerned about the metals elements we will not consider the metals which are the abundant metals like iron and aluminum. They are present in most rocks that we are considering. They contain iron and aluminum as their major element, and what happens to this major element during the process of melting we will not consider in detail, but we know that there will be the melt that forms will also be acquiring this major element depending on their characteristics. We will be considering about metals which are present in trace amount. So, these trace elements could be anything, could be our transition elements, the bulk of this pseudophile element like the precious gold, platinum group metals, could be the base metals copper, zinc, could be silver, gold, could be the high field strength elements, and so on. So, we will have to see what happens to these elements when there is a partial melting process. So, in this method, in these terminologies, we distinguish these elements, trace elements, or during the process of melting. Essentially, we need to, if we consider magmatism or melting as a process of beneficiation, Earth's own beneficiation in converting a common rock to an ore, where the concentration of any element of interest is elevated or is increased to a level that makes it, qualifies it to be called as an ore and to be exploited, then this is essentially has to be looked at as an enrichment process. So, in this we can divide these trace elements into two broad categories. They are the compatible and the incompatible elements of metals. The compatible and incompatible terminology is always coined with respect to, when we understand compatible means we say mantle compatible or mantle incompatible, or in other words we can also put it in this way, that all those elements, all those metals which during the process of melting have the tendency to remain back or stay back in the solid residue. We will call them as compatible metals or elements, and their concentration in the melt which is resulted in this melting process will be lower than what it was in the parent source material which melted. And conversely, all the metals who are incompatible always have the tendency to get themselves enriched in the melt regenerated, and their concentrations will always be higher in the melt compared to what the concentration was in the parent rock or the source rock which melted. So, we will continue discussing on the magmatic process. Thank you very much.